Okay, in this podcast we're going to talk about the kinetic molecular theory, and this is the model that helps us understand gas behavior and what happens as we change conditions. Alright, so the main tenets of the kinetic molecular theory, also called KMT, is that gases consist of large numbers of molecules that are continuous random motion. Now when we say random motion, it doesn't mean that they dance and spin and they twirl around, but they will go basically in a straight line path until they hit something, and when they hit something they get deflected. So they're always running into something, especially the walls of whatever container they're in, be it a room or a box or a cylinder. Okay. The combined volume of all the molecules of a gas is negligible relative to the total volume in which the gas is contained. So what that means is if I have gases in a container, they are so tiny and they are so far apart that the volume they take up is insignificant compared to the total volume. Okay, makes sense. Attractive and repulsive forces between gas molecules are negligible. So what that says is there's no attraction between these gas molecules, and because there's no attraction, there is no slowing down when they hit each other or when they hit something else. So that there's nothing causing this to slow down. So another way of saying this is that the collisions are elastic, which means that no energy is lost. So they don't slow down when they hit each other, or if they hit the side of the containers. All right, so we also know that energy can be transferred between molecules during collisions, right? So one molecule hits another, and that transfers the energy, right? And that can hit another, and that transfers the energy. But the average kinetic energy doesn't change with time as long as the temperature is the same. So if I think about a gas, let's say at 0 degrees C, and I look at the speed of the molecules, I can plot the distribution of that speed, and they're not all going to be the same. Now their average is going to be consistent though. So there'll be some that are moving very, very slow, and there'll be others that are moving quite a bit faster. But on average, their speed's going to be the same. Now if I increase the temperature, I end up with a wider distribution that because I have the same amount of gas, the amount of space, the area under the curve is the same, but the distribution of those particles is spread further, and then I end up with a higher average and a bigger tail, right? As it spreads out, the tail becomes larger, and I have more particles at that higher speed. We also know that the average kinetic energy of molecules is proportional to their absolute temperature. So the higher the temperature, the higher the kinetic energy. Makes sense? The temperature is a reflection of that energy. Alright, so let's take a look at what this means in terms of a real gas, or an ideal gas. A sample of oxygen is compressed to a smaller volume at constant temperature. So here I have a gas. Let's say it's in a cylinder. I'm just not drawing this very well, right? And I take that same cylinder, I don't know why my stuff's coming out crooked, and I push the plunger down so it's taken up half as much space for the same gas. What effect does this have on the average kinetic energy of the oxygen molecules? So what we said is the temperature is not changed. So if the temperature is not changed, the speed of the particles is not going to change, because temperature is a reflection of the speed. So the speed will be the same. What happens to the total number? All right, B, what happens? Okay, so I screwed that one up. Speed question was B. The A question was, what happens to the kinetic energy of the molecules? And the answer is nothing. Again, because the temperature hasn't changed, so my energy hasn't changed, so energy is the same, speed is the same. C is what happens to the total number of collisions of oxygen molecules with the container walls per unit of time. Alright, so here I have, let's say I have 3 particles in here and I have 3 particles in here. There is less container wall to strike for the same number of particles, so my number of collisions is going to go up. And then D is what happens to the number of collisions within a unit area of wall per time. So that says not the whole wall, but let's say a piece of the wall, this area here. What happens to the number of collisions? Well, again, I've got particles condensed in smaller amount of space, so that also will cause more collisions.